And good evening, all our friends on the amateur radio world out there. My goodness, this is Bob DeVance, K5CRX, with the McKinney Amateur Radio Club's last of a series of 10 amateur extra license prep classes. Been quite a journey through these 10 weeks, but I think rewarding, at least we hope so. Tonight, we'll be finishing up our discussion on antennas, finishing up those questions, and then working through feed lines and safety. And there are quite a few questions there, so we will be moving fairly rapidly as we go through the questions. As I said, this is session number 10, the last one, and it's only 2 days now until field day. So looking forward to some folks testing at field day and coming out with their amateur extra radio licenses. Looking forward to that, and I'm quite confident that will in fact happen. In the meantime, if you need to review, of course, the online review questions are wonderful. They'll drill you on what you're weak on, by the way, and make sure that you pick that up so you're able to answer those questions easily. Plus, all of the sessions up to this point are out on the club's YouTube channel. If you want to go back and review any of those or parts of them, for that matter, you're certainly welcome to do that as well. They're there for your convenience. Okay, and with that, we'll be starting just momentarily. Here we go. Recording, so I won't forget it. And there we go. So with that, let me share my screen with you and we'll get it going. We want to go to antennas, and I'm already queued to the right one. And we're going to start the slow. Go. And it didn't take. It started at the beginning. Well, that's life. Hang on a minute. Let me get down here to where we're supposed to be. East. And then I can't find my note again when I look for it. You know, it kind of works that way sometimes. Let's see. E9A12 is what we're looking for. E9A12. And these numbers are not in sequence, as you can probably tell. Okay, let me back up just a second here. I can go by slide number. That'll be a lot easier. We're on slide number 51. There we go. And then go back to full screen. Rats. I've got to do that different. Give me a second. I'm going to get there, I promise. Slide 51, slideshow from current slide. There we go. Now we got it. Have to wrestle it into the dirt sometimes. All right. Here we go. Again, we're using the series where we have the question first and then the answers for discussion afterwards if we need to discuss them. How much gain does an antenna have compared to a half wavelength dipole if the antenna has 6 dB gain over an isotropic radiator? Okay, you'll recall that a standard dipole is considered to have 2.15 dB of gain over the standard isotropic, which has a gain of 1. So if this antenna we're looking at has a 6 dB gain, we subtract the 2.15, which leaves us with 3.85 is the number that's there, the gain that antenna actually has. Okay, and showing you there in the formula. Remember, isotropic has a theoretical gain of just 1. This is showing what the isotropic radiation pattern, which radiates in all directions, versus a gain antenna, which would focus its pattern into one direction. One of the crazy things that sometimes gets confusing for folks is if I put 100 watts into an antenna, and then I put it into a gain antenna with 3.85 dB gain, as it states here, does that mean that I really have got 200 watts going out the antenna? No, that's not what it means. What it really means is that I've taken all that other radiation that would be going in all other different directions and focused it in one direction so that I have a lot more signal going into that chosen direction, which is what the little drawing at the bottom is trying to show. That's a little gain antenna, the antenna radiation pattern showing the radiation going out in one direction as opposed to being scattered all over the place. Okay, what happens as the Q of an antenna increases? Okay, we're talking about Q and bandwidth at this point. You remember, if Q increases, bandwidth decreases. So if the Q increases, the SWR bandwidth is going to decrease. The usable bandwidth would decrease. What is the function of a loading coil in an electrically short antenna? We have an electrical length and a physical length, and they're not always the same because of and boy, it's going to be a hard night for thinking, isn't it? the factor of how fast it travels. There's a name for that. I'll come back to it in a minute. Anyway, function of the loading coil on that. To resonate the antenna by canceling out capacitive reactance. If the electrically short antenna is just that, it will be inductive. So we add the loading coil at the bottom to offset the capacitance, rather, excuse me. Short will be capacitive, inductance will offset that rather. That's showing that coil on the left is one of those big coils that can be used for that. The one on the right looks like it's above a camper, maybe. I'm not sure if the black pole under the bottom of that is supposed to be part of the antenna or not. We'll talk about that a little bit later, because that will come back into play again. Which frequency band has the smallest Fresnel zone? And this is one probably not going to ever run into again, but it's a question that's there. The key to this one is to choose the highest frequency of the list, which is the 5.8 gigahertz. And the reason for that is explained here to some degree. Between 2 points, especially at the higher frequencies, if anything gets in the way of that signal traveling between those 2 points, if something gets in the way that's near the line of sight, which is called the Fresnel zone, that will interfere with the signal and cause the signal to be distorted or to be weakened just a little bit. So 5.8 gigahertz here has the shortest wavelength because it's the highest frequency. Therefore, it would have the smallest Fresnel zone because it has the smallest wavelength. What happens to SWR bandwidth when one or more loading coils are used to resonate an electrically short antenna? Remember, electrically short means it's going to be capacitive. So if we do that, the bandwidth is going to decrease just a little bit of a discussion there. I'm not going to take time to discuss that unless you stop me. If we need to discuss it, by all means, stop me, but we'll keep going. Why should antenna loading coils have a high ratio of reactance to resistance? We want to maximize the efficiency of the antenna. So the antenna loading coils will have a very low resistance, generally speaking. Like that picture of that one there, you notice that's a large coil. It has large windings in it, which will have a very low actual resistance. What's the most efficient location for a loading coil on an electrically short whip? Believe it or not, it's about in the center. And that's if that black part there at the bottom of that antenna is part of the antenna and the big round thing in the middle is the loading coil, then that's showing that. It could be, though, that the antenna above that black thing is actually a helically wound antenna itself. That may actually be the loading coil. I'm not really sure. But loading coil needs to go near the center for that. What advantage of top loading an electrically short HF vertical antenna? Okay, moving the load to the top will improve radiation efficiency. It'll help the signal to get out better. And this is kind of interesting here. Helps to understand if we use a 96-inch CB whip antenna. If any of you ever in CB, you might remember having a really long CB whip antenna attached to the back bumper. It'll not perform well even though you put an antenna tuner with it and try to use it on 10 meters or something like that, because the antenna is not resonant. And because it's not resonant, a lot of power will be lost. We can fool the radio with a tuner into thinking it's matched, but it's really not. The antenna is not resonant, and it's not efficient. It doesn't have good radiation efficiency. Approximately how long is a Yagi's driven element? You remember a Yagi antenna is one of those antennas with several beams on it. How long is the driven element? It's a dipole antenna. How long is a dipole normally? It's a half wavelength. Now, in most cases for the Yagi antennas, we're generally talking about the higher frequencies, i.e., you would not see a Yagi for 160 meters. Those elements would just be too long to be put into a Yagi and put on a rotator. Okay. Basically, as we said, the driven element is just a half wavelength dipole that we're using there. And by putting these elements where we do and putting reflectors behind the driven element, directors in front of the driven element, we can focus that beam even more drastically, shown by the little picture at the bottom, showing how that pattern is kind of concentrated, if you will, over into one direction, both for receive and for transmit. And we'll get later we'll get into the 3 dB points when we talk about some charts. How does radiation resistance of a base-fed whip antenna change below its resonant frequency? When the resonant frequency goes low, the radiation resistance decreases And I'm not sure a good way to remember that. They give a couple of ways to that. I kind of like the second one. Capacitive reactance and ohm reciprocal gives you the formula for that. Capacitive reactance varies inversely with frequency. If the frequency decreases, capacitive reactance increases. So I don't know if that helps any or not, but maybe it will. Why do most two-element Yagis with normal spacing have a reflector instead of a director? Two-element Yagis are the exception rather than the rule. Usually, most Yagis, you'll see at least 3 elements instead of 2, but you can have just 2. And it would give it higher gain if we have the reflector behind it to reflect the signal forward, more so than if we put a director in front of it. Okay, and that's just showing a picture of a Yagi antenna. The driven element there is the one in blue. The reflector, you'll notice, is a little bit longer than the driven element. The directors in front of it are a little bit shorter. General rule of thumb is that the reflector is about 5% longer than the driven, and the directors are about 5% shorter than the driven. What's the purpose of making a Yagi's parasitic elements either longer or shorter than resonance? So that's what that reflector in the back is longer, the directors in the front are shorter. We do that to control phase shift. We do that with the length and with the spacing between the elements. But the answer they're looking for here is the control of phase shift. And there's where the 5% rule comes in there. What is the far field of an antenna? This is just kind of one of those weird things where you can say the longest answer is the one that works. The region where the shape of the radiation pattern no longer varies with distance. It's just the beam's going out and it's not going to change beyond that particular point, beyond the far field. That can also be used for calculating MPE, which is maximum possible exposure. We'll talk about MPE a little bit more when we get into the last session tonight on safety. What does the term ground gain mean? It means having the ground help you. Again, this is one where you can pick the longest answer. An increase in signal strength from ground reflections in the environment of the antenna, i.e. some things are reflecting off the ground and helping the antenna to radiate. What type of analysis is commonly used for modeling antennas? It's called methods of moment software. It's just the name of a software package. One of those, just have to remember it. Method of moments. It works by modeling a series of segments or wire segments that are short segments, basically, all connected together. So the principle that it uses, it takes these wire segments so that it can evaluate each little segment and know what the current is through that particular segment. So it's a wire. A wire is molded as a series of segments or a series of pieces, each having a uniform value of current. And watch it from the last one, which says voltage. This one is for current. Again, that's just the software. The software puts it out there on the screen where you can see it. You describe it. It gives you the information about what the antenna is supposed to do. What's the disadvantage of decreasing the number of wire segments in the antenna model that we just talked about? The standard is 10 segments or more. If you decrease it less than that, you screw up the feed point impedance. Likely the feed point impedance will not be correct in your modeling software. When constructing a beverage antenna, which of the following factors should be included in the design to achieve good performance at the desired frequency? A beverage antenna, I used to think, was probably a whole series of Coke cans tied together somehow. It's not. It's named for the guy whose name was Beverage. It's a very, very, very long wire type antenna. It has to be at least one wavelength long, not a half wave, but a full wavelength long, and oftentimes it's even longer than that. And this gives you a picture of one that somebody set up. The beverage antenna usually is not real high off the ground and is most often used as a receiving antenna, not as a transmitting antenna. The longer the better, and again, it doesn't have to be high off the ground, it just has to be long. You can see the radiation pattern that is receiving there, assuming it's being used for a receiving antenna. It's very, very directional. How can the output voltage of a multiple turn receiving loop antenna be increased? So if we create a loop antenna, which is just a loop of coax or loops of wire, how can we increase that? By increasing the number of turns of the area enclosed by the loop. Just make it bigger. And that's showing a On the left, it's showing a manufactured loop antenna made out of coax, just a loop of coax. And on the right picture is one a gentleman has just made out of using strands of wire wrapped around the frame. You can put more turns on there and make it more powerful. What feature of a cardioid pattern antenna makes it useful for direction finding? You remember cardioid pattern means the signal is going in one direction primarily, means that there is a null or a void in the opposite direction, which is what makes it important. The cardioid pattern has a good null point. So you can see where the signal is coming from and then see where it comes from the least. And 180 degrees from that will be the direction that the signal is coming from that you're looking for. And that's shown by this picture in the lower right. You remember we used that for something else. We're talking about different antennas spaced at different wavelengths apart and so forth. But the cardioid pattern is the middle one there. You'll notice that there is a null on the left-hand side. So from the right-hand side, you'd pick up the signal, then you turn yourself around so that null nulls out the signal. When you get the least signal, you know that the target is 180 degrees away from you or behind you. With the purpose of placing an electrostatic shield around a small loop direction finding antenna. Sometimes we'll use like a pie pan or some aluminum foil or something like that for an electrostatic shield. We put that there. It eliminates unbalanced capacitive coupling to the antenna's surroundings. The key is to remove the depth, or excuse me, to improve the depth of its nulls to make it more accurate in pointing out the direction of the signal that we're looking for, often used for the 75 meter or the lower frequency type signals. What challenge is presented by a small wire loop antenna for direction finding? Again, it's the nulls that kills you. And the small wire loop has a bidirectional or two different nulls, so it can be difficult to determine which null is the right one. Purpose of a sense antenna with a direction finding antenna. It modifies the pattern of the direction finder so that it will only give you one null. It won't give you multiple nulls. It looks something like that. You see that little antenna with an arrow pointing to it there. This is a direction finding antenna system. And that little stub antenna sticking up there is what they're talking about for a sense antenna. What indicates the correct value of terminating resistance for a beverage antenna? We're back to that long antenna again, you remember? Minimum variation in SWR over the desired frequency range. So that there's a resistor at the very end of it that goes to ground, and the value of that resistor will be chosen so that the variation in SWR will be constant over the frequency range that you're using. Again, there's the picture of it at the bottom where you can look at what it looks like. Again, we can't see it in this picture, but at the extreme end of it, there is a resistor to ground. In the pattern shape there, if you look very, very closely, you can see it shows a little resistor there going to ground at the end of it. What is the function of the beverage antenna's terminating resistor? Why do we put that out there? We put it out there so that it will cancel out or absorb signals coming from the reverse direction, the opposite direction from which we're trying to aim it. There's a little bit better picture of a beverage antenna showing the resistor and it going down to ground, and the other end of it being fed through a balun and ground. Anyway, absorbs the back end the back end signal that's coming in that you don't want. What type of radiation pattern is created by a single terminated loop, such as a pennant antenna? And I just have to give you what they say the answer is. It's a cardioid pattern. And this is the picture that they give in the book, that they say this is a wonderful antenna. I've never seen one. I'm not sure how it works particularly, but it supposedly works very, very well. So, what type of radiation pattern by a single terminated loop as a pennant is a cardioid? Okay, what is the 3 dB bandwidth of the antenna radiation pattern shown in figure E9-1? And there's the figure that we're talking about. Okay, if we look at the big lobe on the right, and we follow the circle around to the top, we see we're at 0 dB, or the maximum signal going in that direction. And then you see the numbers going down from the top, very top center, -3, -6, -12, -24 dB. And that's how much signal is being emanated from that particular antenna. They want to know what is the 3 dB width bandwidth points. Okay, so we follow the minus 3 dB circle. That'd be the second circle from the outside around to where it intersects the blue pattern of the transmission of the antenna. And where it crosses there will be that point we're looking at. So it crosses just a little bit less than 30 and a little bit less than minus 30. So between 30 and 30 would be 60. So it's not quite 60. Best answer is going to be about 50 degrees for that. And that's kind of an interpolation thing, as you can see, but about 50 degrees between those 2 points. Okay, just explaining it again. Okay, front to back ratio of the antenna that was shown back there again. And again, we're doing basically the same thing. We have 0 dB going to the right. How many dB do we have showing to the left? Well, the minus 12 dB circle is left of the blue signal pattern. And the minus 24 is a good ways to the right. To me, it looks like it's right in between, so I would have called that 12. But 12 is not one of the answers that they give on the list of answers over there. The answer they're actually looking for is 18. I'm not sure how they get 18 out of that, but what can I say? That's the answer they're looking for. They're looking for 18 out of that one, 18 dB. The front to side ratio of the antenna pattern. Now we're looking at the side. So we look at the side lobes. The top side lobe going up toward minus 12 is not quite 12, and it's somewhere around 18 maybe, would you say? 14 or 18, one of the two. It's actually, they're calling it 14, closer to 14 than 18. Again, that's a judgment call, but the answer they're looking for is 14 dB. Okay. What's generally true, which is generally true for 160 and 180 meter receiving antennas. Key here being receiving, not transmitting. Okay, for the receiving antenna, atmospheric noise is going to be very high. So the directivity of the antenna may be more important than any losses that you might have. I.e., you're not looking for a gain antenna, but you would like to have some directionality for the antenna, is what they're trying to say. What is the front to back ratio of the pattern, radiation pattern shown in figure E92? Well, we're just doing the same thing again. Going over to the back pattern there, the line that it's on is what, about the 30 dB, or just a little over maybe? Somewhere around 30 dB, 28 dB. That's about the closest answer we've got there to that. So we're looking at the 30 dB circle. We're just a little ways away, calling it 28 dB. Again, it's a judgment call, but you have to give them, obviously, the answer they want. How does the radiation pattern of a horizontally polarized antenna? Horizontally polarized normally would mean the antenna is mounted horizontally, i.e., it's parallel to the ground. The radiation pattern of a horizontally polarized antenna mounted above a long slope compared with the same antenna mounted above flat ground. So if we take this horizontally polarized antenna and we point it toward the slope, we will find that the elevation of the signal leaving there will come down with the slope. As it will say there, the main lobe takeoff angle decreases in the downhill direction as the slope goes down. So if you have that choice to go to where you have a slope in your ground, you can direct your signal in that direction if you choose to do so. What effect does lowering a signal's transmitted elevation angle have on ionosphere HF skip propagation? You remember we had a picture of that once before. If we have a low elevation angle, the signal will go out to way out to the ionosphere, bounce back down to the earth a long ways away, as opposed to if we have a high elevation angle, the signal will go almost straight up or nearly straight up, hit the ionosphere and bounce nearly straight back down. It won't go very far. So we want to lower the transmitted elevation angle as much as we can to get longer distances out of that. Distance covered by each hop increases the distance. As a conductor's diameter increases, what's the effect of its electrical length? So as the conductor's diameter, as it gets larger, what does it do to its electrical length? You remember that physical and electrical are a little bit different. It increases. The diameter increases. What's it make it look like? It makes it look like it increases. I don't know an easy way other than just to remember that once again. having to do with velocity factor. That was a term I was looking for a while ago and I couldn't get it to come out. How does the radiation pattern of a horizontally polarized antenna vary with increasing height above ground? Okay, so we're taking that same antenna, putting higher or lower against ground. The takeoff angle of the lowest elevation lobe decreases. So if we move it up higher, the takeoff angle will decrease, and i.e. the angle will get bigger. Decrease is what they're looking for there. And that's in there. We're not going to talk about that. What type of antenna pattern is shown in E92? What type is shown here? What they're trying to show here is the elevation of that signal and where it's going to go over real ground. That the main lobe is going to go down fairly low toward the ground and go out to the 0 point. So it's showing elevation. Then you have some other lobes that will go up a little bit higher and hit the ionosphere at different angles. Okay, shows the elevation pattern. What is the elevation angle of peak response in this particular illustration, E92? Well, we picked the longest one nearest the ground, which is that bottom one, and it's going way out there. And if you know we have 0 degrees on the horizontal line, the first thing going up is 30 degrees, assuming it's about 15 degrees halfway up. So that lowest lobe is somewhere between 0 and 15, maybe 7.5 or 8, something like that. And 7.5 is the closest answer for that. How can two linearly polarized Yagi antennas be used to produce a circular polarization? Again, this is one of those choose the longest answer. Two Yagis on the same axis, perpendicular to each other, with the driven elements at the same point of one boom fed 90 degrees out of phase. That means basically we're going to stack the antennas one on top of the other. What is the effect of adding a terminating resistor to a rhombic or a long wire type antenna? It changes the radiation pattern from bidirection to unidirection, i.e. without the resistor, the antenna will try to receive from both directions. With the resistor, it becomes unidirectional or very directional. And that's showing an actual rhombic, which is a wire spread out like that with a resistor there right in the middle. How much does the gain of an ideal parabolic reflector antenna increase with it when the operating frequency is double? Parabolic antenna, now this is going to be a dish. If we double the operating frequency, we're going to quadruple the gain, which would be 6 dB. You remember that 3 dB is a doubling, 6 dB is doubling it again, or 4 times. 6 dB. And that's a picture of it. And that's the last question, which is a good thing. Okay, we're doing good. Any questions, any thoughts otherwise about that before we hit the next one? We'll keep right on moving.
Hey, Bob.
Yes, sir.
On that rhombic antenna, does it take off toward the resistor or back toward the feed line in the directionality?
As I understand it, it goes toward the resistor. The resistor also helps to cancel out anything coming from the reverse direction.
Okay.
Okay. Good question. All right, here we go. Feed lines and safety. We're doing good. We're going to go fast, but hopefully it'll be good. Here we go. Which matching system for Yagi antennas requires a driven element to be insulated from the boom? When we create that Yagi, we put the driven element up there. Some systems let you attach that metal center element directly to the boom. Others require that it be insulated. So to use a beta match or a hairpin match, as it's sometimes called, the the driven element has to be insulated from the boom. It can't be attached directly to the boom. It has to be attached through insulators. And I've got a picture later on there. It shows a hairpin match. What antenna matching system matches coaxial cable to an antenna? By connecting the shield to the center of the antenna and the conductor a fraction of a wavelength to one side. And that's going to be the gamma match. And I've got a picture of that one coming up as well. There's one right there. That doesn't show the whole gamma match system, but if you look at that, you see the place where the coax connector goes in. Slightly to the left of that, you'll see that into the center pin of that connector is connected to a little aluminum rod that's inside a plastic tube, which is again inside an aluminum tube. That is a capacitor. And then that overall aluminum tube goes out there, usually about 8 or 10 inches, and is attached to the element that's right above it there in that picture. And then to adjust the match of the antenna, you would move that little contraption in or out over that intersection with the plastic tube over it to change the capacitance and get the match that you need for a gamma match. I kind of it doesn't really look like the letter G, but it kind of does look like the letter G to me there. That's how I remember what a gamma match looks like. Okay, we're not going to go into that one. We just don't have time. What matching system uses a short length of transmission line connected in parallel with the feed line at or near the feed point? And this is going to be a stub match. Use a stub of transmission line in parallel with the feed line, and that's used to cancel out the whatever it needs to be canceled out there, capacitance or reactance, to give you a good match. Purpose of a series capacitor in a gamma match. That's that little sliding tube thing that we talked about. Its purpose is to cancel unwanted inductive reactance, and that's usually the case with antennas. If they're inductive, we put a capacitor. If they're capacitive, either short, then we'll put inductance in there to compensate for it. What Yagi-driven element feed point impedance is required to use a beta or a hairpin matching system? This hairpin is a little bit different from what we've talked about so far, but we're assuming that it's going to be capacitive, and it looks something like that. There's a little piece of wire that goes out, kind of as you see there, between the two driven elements. It looks like a short to us, and it is a DC short, but to VHF or UHF, it sees it instead as a matching network. Okay. What parameter describes the interaction of a load and a transmission line? Where the two come together, it's the reflection coefficient. That's just one of those terms that you'll see come around from time to time in the Smith chart and various other places. Reflection coefficient. A mismatched transmission line will give you reflections, hence the reflection coefficient. A Wilkinson divider, what in the world is that? It's a divider that lets you feed two 50-ohm loads with one 50-ohm transmission line. Divide the power equally between two 50-ohm loads, maintaining the 50-ohm input impedance from your feed line. And it looks something like that. That's how they're put together there. We'll have some kind of a little loading resistor or some device in there, matching device on each leg, and then a resistor between the two so that both antennas are at 50 ohms and the input remains at 50 ohms. That's the idea behind it. Which of the following is used to shunt feed a grounded tower at its base? Use the gamma match for that. And you can do that with all kinds of things. We're not going to talk about the what ifs there. Which of these transmission line impedances would be suitable for constructing a quarter wave Q section for matching a 100 ohm feed point impedance to a 50 ohm transmission line? So we want to do a match there. We use a 75 ohm piece of line to do that. What is the purpose of using multiple driven elements connected through phasing lines? Okay, control the antenna's radiation pattern. You remember when we talked about the distance between two antennas being a half wave or a quarter wave or eighth waves and all those different things? We could tune that thing to make it be whatever we wanted. So we can use the phasing to control the radiation pattern and how it's going to be, how the signal's going out. Which of the following is a significant difference between foam dielectric coaxial cable and solid dielectric coaxial cable, assuming all other parameters are the same? Okay, foam dielectric is what's used in RG58 cable, which is one of the least expensive coax cables. It's good because it bends well, it's very pliable, it's very flexible. You get into the really good stuff, the Heliax cable, they will have a solid dielectric, solid plastic of some kind. They don't bend well, they don't deal well with curves. Some coax even is like that. So what they're saying, what's the difference though between those dielectrics? All of these things. The foam dielectric has a lower safe maximum operating voltage. It's foam. It has air in it, so it doesn't insulate that well. The foam dielectric has a lower loss per unit of length. It has a higher. Wow. The dielectric coax cable has lower loss per unit of length. If we use the solid, is what they meant. I think it's what they meant. They got that backward. Foam dielectric coaxial has a higher velocity factor. Anyway, all of the answers is what they're looking for. This is showing a piece of heliax down there in the lower left. And the insulator, you can see the dielectric behind that is a solid plastic of some sort of stuff there. We're not going to argue with them over their answers that they want. And this is just FYI, some different coax types, the size, the loss at 100 megahertz at 100 feet of that cable, the loss at 400 megahertz. So if you have 400 megahertz of RG58U, that's the cheapest cable. It's easy to handle and all that. But at 100 megahertz at 100 feet, you're losing 4.3 dB. And at 400 megahertz, you're losing 9.4 dB. So you've lost over half of your signal when you go with 400 megahertz on RG58U versus the hard line down there, the good stuff, the expensive stuff, very little loss by comparison. That's just for your information. What is the velocity factor of a transmission line? You'll remember that a wave in free space travels at the speed of light. When it travels through a conductor, it slows down. The velocity of the wave in the transmission line divided by the velocity of light in a vacuum. In other words, we take how fast is it actually traveling divided by the speed of light to get the velocity factor. Okay. Which of the following has the biggest effect on velocity factor of a transmission line? The velocity factor of the speed with which things go through is going to be the dielectric. Depends on how much capacitance that dielectric creates inside the coax as to how much it slows the signal down. And again, showing that same loss chart we saw before. Which of the following can cause shielded cables to radiate or receive interference? And we talked a lot about that in a lot of places about common mode currents using various balance and other things to cancel out common mode currents in the shield. And that's what we don't want. We don't want common mode current. So if you get common mode current, it can cause the coax line to actually act as a radiator or receive antenna. What impedance does a half-wave transmission line present to an RF generator when the line is shorted at the far end? Okay. So we got a half wavelength of transmission line. We're feeding it with an RF generator. That could be a radio or it could be an actual signal generator. If we short at the end of the extreme far end of the line, then the RF generator would see a very low impedance. This has a lot to do with a lot of different things, and we'll explain more as we go along. And the different places where we put the short or where we put the open also affects it. And there's a little mnemonic we'll get to here in a minute that will help you remember it. Okay, short at the far end, we have very low impedance. Electrical length of a coax cable, or why is the electrical length of a coax cable longer than its physical length? And it has to do with waves traveling through it more slowly in the cable than they would travel in air. That's the velocity factor. A microstrip. What is a microstrip? Again, you pick the longest answer. Precision printed, yes, right on. Printed circuit conductors above a ground plane that provide constant impedance and interconnects at microwave frequencies. You'll see these little handy-dandy little circuit boards with certain traces mapped out on those that can act as a conductor to minimize any impedance and minimize the capacitance as they go across the board. Okay. What is the approximate physical length of an air-insulated parallel conductor transmission line that's electric 1/2 wavelength at 14.1 megahertz? So we're talking air-insulated line. We're talking about a ladder line here, basically. And we're saying, what's its approximate physical length? 10.6 meters. Now, we can do this kind of backward. 14 megahertz is 20 meters. Half a wave at 20 meters is 10 meters. So it's going to have to be somewhere close to 10 meters, half a wavelength. 10.6 is the only thing close to that, so that you can do that by process of elimination. You can also do some calculations and come up with some other ideas. That 984 is a standard number for calculating lengths based on a one wave wavelength. Half of that for a half wave, a fourth of that for a quarter wavelength. And of course, as I said, they'll convert feet to meters if that's what you're working with. I always have to watch out for the conversions. How does a parallel conductor transmission line compare to coaxial cable in a plastic dielectric? Okay, the parallel conductor, the ladder line will have lower loss, generally speaking, than any coax will have. Okay. What impedance does a quarter wavelength transmission line present to an RF generator when the line is shorted? This is related to that previous question we had there. This time we got a quarter wavelength and the line is shorted at the end, presents a very high impedance. And again, we've got a way to remember that in just a second here. And then an eighth wavelength line, when it's shorted at its far end, will be an inductive reactance. Hopefully I'm going to get to this formula here in a second. Then an eighth wavelength line again, when it's open now at the far end, will be capacitive reactance, which makes kind of sense. An eighth wavelength is a very short piece of transmission line, and essentially it's two conductors, just like the plates inside a capacitor. So it's going to be capacitive and provide capacitive reactance. Okay, more of that. Impedance does a quarter wavelength have, and when the line is open on the far end, it's going to be a very low impedance. Now then, this is what I was looking for. You can use the little mnemonic, I like zucchini crumpets, whether you like crumpets or not, whether you like zucchini or not. But you're trying to remember I, L, Z, and C. Okay, I represents infinity, L represents inductance, Z represents zero, and C indicates capacitive. So one more eighth length. When you go backwards a little bit, you start all over again as it explains it there. If you have the ARL book, you'll find this chart that's there. But at any rate, this is one of the little ways that you can help to remember what's going on with that. And I thought I had an example for that, but I really don't right now. I can't give you a better explanation than that. Gosh, that bugs me. I can't remember exactly how they were doing it. How the impedance along opening the transmission line changes as you move from the opening of 1/8 wave segments. That was the key. 1/8 wave segments. So if a quarter wave antenna would be 2 1/8s. A 3/4 wave, a half wave, etc., is based on the number of eighths, and we go for each eighth of a wave. And 1/8 out, excuse me, is I. It'll be infinity. It'll be very high resistance. Put another section in there, becomes inductive. Put a third eighth of a wave in there, becomes zero or short. Put another eighth of a wave in there, it shows up as capacitive. That's the idea behind that particular thing. If you want to snap a picture of that with your cell phone or something, if you don't have that, that's good. If you need me to, I can actually take a shot of that and email it to you, if that'll help you. It may create more confusion than it helps. I'm not sure. Which of the following is an advantage of using an antenna analyzer compared to an SWR bridge? The SWR bridge was a very, very old instrument that we used to use for computing SWR, where you had to do a lot of adjustments and measurements and various things, where the antenna analyzer, you just go measure it and you get a reading automatically. So antenna analyzers compute the SWR and give it to you automatically, instantly. You don't have to do a lot of knob twiddling and computations. Okay. Which of the following is used to measure SWR? Well, you can actually use all of those things. You can use the directional wattmeter, see what's forward and what's reflected of the signal going to the antenna. Use a vector network analyzer, which will also tell you what's going out and what's being reflected. And the antenna analyzer will do the same thing and convert those readings to directed to SWR. All the answers are correct. And there is an antenna analyzer. That's the Comet CA500, which I have. It's a very fine instrument. On that particular instrument, the needles at the top, one gives you the SWR, the other gives you the impedance. So you'd be looking for a low SWR and a 50 ohm impedance if you can come up with that. And then the little display on there gives you additional information, lets you know whether the impedance is capacitive or inductive, etc. But okay. Smith charts. Oh boy, the plot is getting ready to thicken. Buckle your seatbelts. I'm going to take a quick side trip for this, so stay with me. Okay, I'm going to try this and hope this works. Okay, now I have two things on the screen. Let's see. Screen sharing is paused. Share that. Okay, can you guys see two pictures on the screen?
Yes.
See a document and a drawing?
Yes.
Okay, good. That's what I was hoping for. What I wanted to do with this is talk about the questions that regard the Smith chart, because there are 12 questions on there that deal with this. And it's not something that I deal with every day anyway. And I am not good with Smith chart. I mean, I know what it is, and I can define the terms. So what I want to do is just go through this first and define terms with it. And then we'll go through the questions very quickly as they will reflect this. Now, again, if you want to take your phone, take a picture of this, feel free to do so, or I can email it to you if you want it. But the questions on the left are the actual questions and answers as given in the ARRL manual. That's the 1-inch thick one that comes with all the questions and answers. And then the picture on the right is just a picture I got off the internet of a simplified Smith chart. A real Smith chart has dozens and dozens more lines and arcs and circles and all that than that shows there. But this little picture will serve the purpose. Okay, looking at the picture, the straight line that goes through the center of that thing is called the resistive axis, or the resistance line. It's the only straight line in the whole chart. You'll notice the number 1 right about in the middle. That's called the prime center, where that circle crosses the 1 on the resistance axis. Around the outer circle, the big circle at the very outside, the top half of that circle is impedance. The lower half of that circle is capacitance. We could relate that to our regular chart that we did before. You know, this is the standard Cartesian coordinate type charts. On that chart, we had resistance on the horizontal line through the center, and then going straight up the y-axis going up, we had inductance. We had capacitance going straight down. So if we took that y-axis and wrapped it back around to the beginning, that's what it would look like in this picture here called a Smith chart. We basically just taken the y-axis at the top, bent it all around to the right down to the infinity point, taken the capacitive reactance from the y-axis going down and bent it all the way back around to infinity. So that's how we came up with this thing. And that's kind of what we're looking for. Okay, so let's just run through the questions here, and I think this hopefully will make more sense. Which of the following can be calculated using a Smith chart? Impedance along transmission lines. Now, the impedance along a transmission line, if there's nothing at the other end of it, can be constant, as opposed to when there's something attached to it where the current and the voltage are out of phase. But the Smith chart will help us calculate those things. Impedance along transmission lines is the answer for that question. What type of coordinate system is used? They use reactance circles and resistance circles and reactance arcs. Again, if you look at the number 1 in the picture, you'll see there's a circle there that circles all the way back around to infinity. Those are resistance circles. The arcs that go from the infinity point out to the outer ring, those are called the reactance arcs. Represent different reactants. Top represents inductive reactance. Bottom half of the circle represents capacitive reactance. On the Smith chart of 9.3, which looks something very similar to this, what is the name for the large outer circle on which the reactance arcs terminate? That's the big circle all the way around the whole thing there. That's called the reactance axis. That's the same axis we had in the rectangular coordinate system, where the y-axis went straight up for impedance, straight down for capacitance. We've just bent that axis around to where it makes a circle. Let's see, on the Smith chart out there, what is the only straight line shown? And you can look at it and see the only straight line there is the resistance line that goes right through the middle. And by the way, sometimes you'll see this thing rotated 90 degrees or 180 degrees. So don't let that throw you off. The resistance line will still be the straight line. How is the Smith chart normalized? And the answer is reassign the prime center's impedance value. Well, what we basically wind up doing is we say, okay, we're going to use 50 ohms as our base impedance, which was what we worked with in amateur radio. And so we're going to call the one there, that's going to be our 50 ohm impedance point. But in order to make that happen, we would divide 1 by 50, or whatever our real impedance was, by 50, which would give it 1. There's a little formula, a little dance that you do with that that's called normalizing. So you get the numbers down in small value numbers that are easy to manipulate. That's all that really boils down to. Normalization, assigning the prime center's impedance value. We're just prorating that out to something we can deal with. What is the third family of circles often added? Now, this third family of circles is not showing here, but they're constant SWR circles. So we can plot SWR with these things and put an additional circle that would show all the SWR points on that particular item that we're measuring. What do the arcs represent? Constant reactance, either capacitive or inductance. You see we have plus J at the top and minus J at the bottom for plus inductive minus capacitive. And then in what units are the wavelength scales on a Smith chart calibrated? And this is one you just have to remember. In fractions of transmission lines, electrical length, not physical, but electrical length. And in the true Smith chart, you'll see not only these circles, but below it, there will be an additional calibrated scale, which you can use with a ruler with a straight edge. And once you get plots pointed on the Smith chart itself, you can drop a straight line down and get the actual SWR reading from there and a whole bunch of other things as well. So my point behind all this is, these are the questions that have to do with the Smith chart. With 12 questions out of the 600 being list, you can pretty well count you're going to get at least one of the questions on the Smith chart on the test. So we want to be ready for that. That's why I want to do it that way. And let's say I'm going to save that and close it and go back to here and slideshow from the current slide and go on the current slide. There we go. Okay, we're back to where we started from. So now we're going to go through these questions fairly quickly. Which of the following can be calculated using the Smith chart? Impedance along transmission lines. And I just put that little picture over there so you'd have a reference point. Those are not actually on the test. Which of the following is a common use for the Smith chart? Determine the length and the position of an impedance matching stub. Smith chart was, what type of coordinate system is used? It's using resistance circles and reactance arcs. You'll remember the circles are the resistance and the arcs represent reactance. Which of the following is often determined using the Smith chart? Impedance and SWR values in transmission lines. By the way, the Smith chart is often used mainly for transmission lines, more so than for antennas and such itself. What two families of circles are out there? You have the resistance circles and you have the reactance arcs. By the way, those reactance arcs, if we carried them all the way around and made a complete circle, they would eventually make a complete circle and come back to infinity outside the big circle. On the Smith chart shown, that's the actual picture. What is the name for the large outer circle, that big circle around the whole thing? That is going to be the reactance axis. You'll remember the straight line. This is where I was talking about they've rotated it 90 degrees. The straight line goes right straight through the center, goes up and down. That's the resistance axis. The circle that goes around the whole thing is the reactance axis. On this chart, what is the only straight line there? Going to be the resistance axis, resistance line. How's the Smith chart normalized? Reassign the prime center impedance value. You know, they've got a pretty good mix of answers there to try to mess you up. Prime center impedance. Third family of circles that's often added is constant SWR circles. We can have circles that represent SWR on top of the Smith chart. What do the arcs represent? Constant reactance. It can be either it can be either inductive or it can be reactive. Points of constant reactance. What are the units? In what units are wavelength scales calibrated? You remember it's the electrical wavelength that we're looking at there. Okay, That's the questions on the Smith chart. Any questions on that before we go on? I know that's drinking from a fire hose and covering it fast. Again, if you'd like to have that, I'd like to put that in Word. I can easily email that to you if you'd like to have it. Okay, going on. We've got about 5 minutes left. Let's see how far we can get. When evaluating a site with multiple transmitters operating at the same time, the operators and licensees of which transmitters are responsible for mitigating overexposure situations. Each transmitter that produces 5% or more of its maximum permissible exposure limit in those areas where the MPE limit is exceeded. So each transmitter that has that has to be evaluated individually. Which of the following types of equipment are exempt from RF exposure? And this is just one of those crazy things. It's in the rules, handheld transceivers that were sold before May 3rd, 2021. Let me back up one. There's something important on the bottom of that one. ARRL provides an exposure calculator that you can use. Technically, we are supposed to do this exposure calculation for our ham sites, and you can use this calculator rather than doing actual measurements, and that's acceptable by the FCC's definition. When must an RF exposure evaluation be performed on an amateur station operating 80 meters? Always. It's operating, it's supposed to have an evaluation performed. Didn't say how often, just says we're always supposed to do one. And again, there's the link to that calculator on ARRL. What hazard is created by operating at microwave frequencies? Microwaves, the high gain antennas that they have there, can give us high radiation levels because these signals are composited or close together. They're amplified, if you please. They can burn you. They tell me, unfortunately, I've never experienced it, and I hope I never do, that the first symptom of microwave burning for you, you'll feel your eyeballs start to get hot. If you're ever in a situation in front of an antenna and you feel part of your body getting hot, that's a danger signal. Move quickly. In some places, you may even see warning hazard signs like that. Over what range of frequencies are the FCC human body exposure limits most restrictive? 300 or 30 to 300 megahertz. Of course, that's a lot of where we want to operate, isn't it? SAR. What is SAR? What does it measure? The rate at which RF energy is absorbed by the body, and then we get the definition, specific absorption rate, the rate at which energy is absorbed. When evaluating RF exposure levels from your station at a neighbor's home, what must you do? Ensure signals from your station are less than the uncontrolled maximum possible limits. And uncontrolled means that it's a place that's out of your control. And so you assume that they're out of your control, so you want to make sure that you're not doing anything bad to them. You don't want to aim your beam straight into their house and pump out 2,000 watts. Why are there separate electric and magnetic maximum permission exposure limits at frequencies below 300? Body reacts differently. And ground reflections can cause the field strength to vary. The NH field radiation intensity occur at different locations. They bounce off of different things and be affected by things that surround them, all of the above. Which of the following additional rules apply if you're rating an amateur antenna structure at the site on or near a public airport? You got to watch out for how high your antenna actually is. You might have to notify the FAA, depending. The key is 200 feet. If you exceed 200 feet, you have to register it with the FAA. If it's close to 200 feet, it's a wise idea to register it with them anyway, just to be a good citizen. What is meant by 100% tie-off regarding tower safety? At least one lanyard is attached to the tower at all times. Your climbing harness, now we're talking safety. The climbing harness that you use when you climb the tower has 2 lanyards attached, and one of those lanyards should always be attached. As you're going up the tower, you'll take one lanyard and attach it above your head. Then you can detach the second one, move it up above your head. So one is always attached while you're attaching the second one there. And that's showing, you can see that the guy whose back is to us there in the picture, you can see he has those 2 yellow lanyards that he has there. He has one tied off on his right. The other is in front of him. I can't tell if it's tied off somewhere or not. It may or may not be. But as you're climbing, you use those two lanyards. To what should lanyards be attached? You go right to the antenna mast itself, not any of the brackets, not any of the rungs of a ladder or whatever. You go to the tower legs because they're most stable. Where should a shock absorbing lanyard be attached to a tower working above the ground? You want it up above your head. So it'll catch you if you fall without your having to fall too hard and too far. And you can see this guy here. He has one lanyard attached to that cross piece and another attached way up above his head. So in this case, he's double protected there. What's the purpose of a single point ground panel? The idea is you have a ground panel inside your shack and all grounds emanate to and from that. If you do that, then all lightning protectors would activate at the same time because all the lightning arresters in your different coax cables would be at the same potential for the lightning, and they would all go to ground at the same time. All lightning protectors activate simultaneously. And believe it or not, that's the end of it. Stop the share. Okay, gang, breathe. What do you think?
Well, that made sense.
Okay. I know we were going like a whirlwind there. I do understand that. So let me stop the recording there. At least we did get a recording of all of that.